All right, so we've talked about angle bisectors, the orthocenter, and perpendicular bisectors. We've got the circumcenter, right? We talked about the circle that goes all the way around, touches all the vertices. And so if this is a circle, we've got from G to A, those are radii. So those are all going to be the same length. We didn't get to medians, though. So medians connect vertex to midpoint. And the center, G, that point right there, we call the centroid. If you were from Eastern Europe, you call it the medicenter. Actually, that's what I call it because I am from Eastern Europe, of course. No, I just like medicenter better because it sounds like median. It helps me remember what goes with what. Well, what's really going on here is that this point, it's special properties, and then it's the balance point of the triangle. So if you wanted to balance that triangle on your finger, that would be where you put it, right? And the way to find that, again, is to connect midpoint to vertex and find the intersection. So this is the center of mass. Cool. So, just something interesting. What do you notice about all these diagrams? First of all, they're all the same triangle. They just have different segments drawn in them. What else do you notice? What? Good. What else you got? What do you mean? They do. What else you got? How about this? I'm going to draw a couple lines randomly. Okay? Closing my eyes. They're lines, so they go on forever. So will those two lines intersect? Yes, we should not be surprised by that, right? For two lines not to intersect, what do they have to be? Parallel. And the odds of me drawing parallel lines randomly, pretty rare, right? So for two lines, the concurrency is pretty likely. We call it concurrency when they intersect, right? That's the point of concurrency, is where they intersect. So that would be this point right there, right? So the likelihood of them being concurrent for two lines, very likely, right? It'd be almost impossible to draw two perfectly parallel lines blindfolded. What about three lines? Right? Well, cool. If we take two at a time, we shouldn't be surprised that they intersect, right? We talked about how two are very likely to intersect, right? These two would intersect eventually, right? Here. And then these two would intersect eventually here. Something like that. So yeah, two at a time, we should not be surprised that we have concurrent lines, right? That they intersect. But for all three to intersect, we'd need something like this. And good luck drawing that blindfolded, right? So for three lines to be concurrent, it's actually really rare. Nope. These ones that I just drew right here. Right here. Yes, this right here would be concurrent. This works, but I drew that with my eyes open. Drawing that with your eyes closed, perfectly intersecting all of them, is very difficult. Right? Two at a time, no big deal, right? We get two at a time all the time. That happens pretty often. But to get all three to intersect at the same spot, very, very rare, right? Which is why, when we see something like this, a bunch of seemingly random lines, right? We have angle bisectors of a triangle all intersecting at one point. Orthogonals all happen to intersect at one point. They're concurrent. For perpendicular bisectors all to be concurrent, right? For that to happen is pretty rare. Now the question is it just these special triangles that I've given you, or are they always concurrent? Do we always get these points? So we're going to investigate that. Behold. GeoGebra. All right, we need to name this last point. Everybody say hi to Nellie. All right, what are we going to name this last point? Bailey.
Yeah. Pod. Name it Pod. No, I just spelled my name wrong. So
So, looking at your sheet, which one do you want to do first? What center do you want to create first? We have 4 different ones. We've got the in-center, the circumcenter, the orthocenter, and the medicenter or centroid. The orthocenter. Okay, great. What lines do I need to make to find the orthocenter? Orthogonals, right? Perpendiculars, right? That's what it says in your paper. All right, so orthogonal. So I'm going to go to the perpendicular tool, and I'm going to create a perpendicular line. So what I'm going to do is I'm going to go from here and drop a 90-degree line. So I'm going to click Jacob, and I'm going to click this line, and I'm going to make a perpendicular between there and this line. So that's 90 degrees right there. I can pull up my angle measure tool and prove it to you, but just trust me, okay? So we've got a perpendicular, this guy right here. I'll change its color so you can see it, okay? Now, it's at the intersection of all the perpendiculars, so I'm going to go from here and find the perpendicular to here. So that hits it at 90. Oops. I don't want a perpendicular there. And where they intersect is here. Now, this should not be surprising, because 2 lines intersecting happens all the frickin' time, right? But for all 3 lines to be concurrent is pretty rare, so I'm going to make that last perpendicular from Khalil. Shout out to my boy Khalil. Best of luck, my man.
Wait,
To here.
I thought it was Khalil.
I don't know. Nelly never told me how to pronounce it. And look, they do all intersect at one point. So this point is our orthocenter. Now, this triangle is very similar to the one that I gave you on the paper, right? It's a cube. So what I'm going to do is I'm going to drag this around. Equilateral, or close to it at least. If you see equilateral, it's like right in the middle. If I go and make it acute, or I'm sorry, obtuse, where does the orthocenter end up? On the outside. The reason for this is kind of complex, but if you think about it, the orthocenter is all the height of the triangle. And the reason these lines go outside is because the height of this triangle is from here to here, right? You ever seen a diagram like that where it has the triangle and it has to draw the height outside it, right? And those are weird looking. Well, it's because it's obtuse. So the height from here goes out. Same thing here, if I were to rotate this, the height would go this way. I would have ground here, and I'd be finding a 90-degree angle with that ground. So from here to here, that's the 90, connecting with this line. So that's the ground that it's sitting on, and this would be the height. So they go outside. This one obviously has the height right here, no big deal. But it ends up going outside. So when the triangle's obtuse, the orthocenter is actually located outside the triangle. When it's acute, it's inside. And then when it's a right angle, as I think you've already seen, right? It's a right triangle. Where does it end up? The vertex of the 90-degree angle, right? And the reason for that is because, remember, orthocenter is the height. So now you do a 90-degree triangle, isn't this segment right here the height? Right? So there's one height. If I turn it, isn't this guy the height? So of course they intersect there. So for a acute triangle, it ends up on the inside. For a 90-degree triangle, it ends up on the right angle. And then as we push further, it ends up on the outside. So let's mark that on our diagram. So orthocenter. When we have an acute triangle, it's on the inside. For a 90-degree triangle, it ends up right on the 90-degree vertex. That makes sense, right? Again, the height of the triangle is what we're connecting, and the height of this 90-degree triangle is this length, right? If I were to rotate that triangle so it was sitting the other way, this would be the height, and so where the heights intersect is here, right? The third height goes this way, but 2 of the heights intersect right there. The height of this triangle I would measure just from here, right? So they would all intersect in the center, just like this guy. And then for an obtuse triangle, obtuse is kind of hard to draw, so what I'd always do is draw a flat line and then extend it really far back. We know that it'll end up outside. Now, will it be behind this triangle, like down here, or will it be up here? Which side will it be, on the top or the bottom of this triangle? The bottom, right? You can kind of see as we move, we go further and further this way, right? Towards the right angle, and then further out. So this ends up on the outside. You will need to know where these occur for these 3 different types of triangle. Again, the idea of this one, as the 90s, as the heights keep moving further and further away, right? We end up outside the triangle. You can kind of see the progression. Inside towards this angle, now it's a right angle, so it's right on it. And as we extend that angle even more, it keeps pushing it away. Okay? I'll show you that one more time. No one cares, Bailey. All right, so inside the triangle acute, and as it becomes more right, it keeps pushing it in that direction. So naturally, it's going to go outside the triangle if I keep extending that angle. Are we cool with that idea? All right, so the orthocenter, depending on what triangle we're talking about, has a different location. Sometimes the center of this triangle isn't even in the triangle. All right, cool. Let's make another one. Oh no. This is important.
You don't like Jacob.
I love Jacob.
Jacob. All right. So, pick another center you want to make. We already made the orthocenter. Give me another one.
Circumcenter.
Circumcenter. All right. What things do I need to make the circumcenter? There's a joke here, right? You go to the orthocenter to get your orthodontist stuff done. You go to the circumcenter to get what done?
Circumference.
That's right. Circumference. Yes.
Wow.
I didn't make the joke the other day.
All right. So, I need perpendicular bisectors to make it, right? So what I'm going to do is I'm going to find the midpoint of all my sides. Those are my midpoints. And then I'm going to connect a perpendicular line from that midpoint 90 degrees. Now, with that line, remember I want to go from the midpoint straight up 90, so I click the same line to show that I have made a 90 with this line. Does it go through the top? No, that happens, right? This is weird looking one. I want a 90 degree from here. So that's going to be like that. I want a 90 degree from here. So it's going to click that point from that line. And notice they do all intersect, but this is an acute triangle. What happens if I make it a right triangle? Where does it end up going? It goes to the midpoint of the hypotenuse, right? And as we get bigger, where do you think it's going to go? Outside. Now it goes the opposite direction of the orthocenter. Turns out the orthocenter and the circumcenter will always be in opposite spots. They're always across from each other until they perfectly intersect at the same point. So, when it's obtuse triangle, it ends up on the outside, kind of like a satellite, right? Like a satellite dish. And when it's 90, it ends up on the midpoint of the 90 or the hypotenuse. And acute is on the inside. Let's write that down. Write that down. Write that down. All right. Acute inside. 90 degree, it ends up on the midpoint.
Which one is this?
Perpendicular bisectors, the orthocenter, or the circumcenter. Midpoint of hypotenuse. And then when it's obtuse, does it end up on the top of this triangle or on the bottom? On the top or on the bottom? Well, if you follow it, as we go from acute to right, we're going in this direction. So it's going to keep pushing it out this way. So it's going to be on the top of this triangle, right? Outside. You will need to know this stuff. I posted a video on Google Classroom that might help you learn more about it and get used to it. What do you want to talk about? Angle bisectors in the in-center, or do you want to go to medians and medi-center? All right, inside, on the midpoint of the hypotenuse, and then the outside. All right, let's talk about angle bisectors. All right. Deleting all this stuff. I'm going to create some angle bisectors. So I'm going to click Jacob, Bailey, Lee, he, and now I've bisected that angle. I'm going to bisect this one. Remember, the vertex has to be the middle one, so I bisected this angle. They intersect at a point. No one cares. 2 lines intersecting happens all the time. But when 3 lines do, it's pretty rare. All right, so it's acute. Now, remember, the angle bisectors all intersect to form what center? What's the name of this center?
In-center.
The in-center, right? So what do you think is going to happen? Remember, what does the in-center actually do? What is the in-center? It's the center of what?
Inscribed circle.
Inscribed circle. So what do you think is going to happen as I make it a right triangle? Is it going to move out of the triangle? Is it going to what?
Move out. I don't know.
I think it's gonna stay.
Oh, no.
It stays in. What do you think is going to make it happen when I do obtuse? Because it's the center of an inscribed inscribed circle, right? The circle's inside of the triangle. So how could the center of the circle be outside? Do you see what I'm saying? If the circle's always inside the triangle, and I'll show you. Let me do a hypotenuse or a perpendicular so I can find my radius.
Oh my gosh, it was that.
Negative 2.0.
We can open it every day.
Right. Oh no.
Oh my gosh.
Stop it. Oh my god.
Yeah.
I swear to God.
Yes.
There we go. There's my radius. Bailey, shut up. No one cares. All right. So the circle's always inside the triangle, which means the center of that circle should always be inside the triangle. That should come as no surprise. So it's always in the center. The circle's always in the center, no matter what we have. All right. So when we're talking acute triangle, it's on the inside. Right triangle, it's on the inside. And for an obtuse triangle, it's also on the inside because that circle is inside the triangle, right? So we should not be shocked about that. The incenter is always on the inside because the inscribed circle is always on the inside. All right, I'm moving on because I hope that you can copy down inside for all. Let's talk about medians in the centroid. All right, what segments do I need to make the centroid or the many-centered? Try again.
Angle bisectors.
We just did angle bisectors to the in-center. We're talking about the centroid. How do I make the centroid?
Put it in the center.
Also known as the many-center. Which center? Triangle has 4 different centers.
I don't know.
The circle one.
Median.
Medians, very good. And what is a median?
How are we supposed to know this?
It's literally written down.
I'm literally. Can this be an open notes quiz?
Nope.
That's a great idea.
What was the question?
What's a median?
Vertex,
The
mid.
thing.
Vertex to midpoint. Thank you. So I'm going to find my
How do
midpoint.
you know that?
Yeah. Then
Just
no.
reading it off the paper.
Literally on the paper.
My mom says I say literally too much, so I start saying hypothetical.
Well, literally, in this case, is literally the word I want to use. Because it is not figuratively on the paper, it is literally on the paper.
She says I say like too
Bow
much.
down to
Okay,
Moses.
now I say as though instead of like.
Alright, so there's our centroid slash many-center. Now, what is the centroid? Like, what are its properties? We didn't write many. What does centroid actually do? What's the point? Yeah, go ahead. Center of mass, right? It's the balance point. So on this ruler, the balance point's in the middle, right? Because it's well balanced on both sides. If one side was heavier, I'd have to lean towards that side to balance it out, right?
Yes.
Will the center of mass, the balance point on a ruler, no matter how heavy I make one side, will it ever be off the ruler?
No.
No, you're not going to balance anything like that. Come on. So on this quiz on Friday, I better not see somebody say, oh, the centroid's outside the triangle sometimes. It's the center of mass. How can it be balanced outside? Right? I'm going to balance this pen. Oh, man, good attempt.
I will find it.
Right? So you shouldn't be shocked when I drag this around and go from acute to right to obtuse, that it's still in the middle. Now, again, the larger I make one side, right, if I pull it far away, it pulls the center of mass with it because I've made that side heavier, right? Now, we've already learned about the centroid a little bit. We've connected 2 of these up. And we found out that the relationship between this part and this part is double. Same thing here, always. We proved that last week. We're going to prove it again next week. For real, you actually know what we're looking at here. But the centroid always divides up the medians into 1/3 and 2/3, otherwise known as half and double. So if that's 3, this would be 6. And if that were 5, this whole thing would be 10 right here. So should we be shocked that the centroid is always inside the triangle? No. It's the center of mass. Inside, inside, inside. Last week we talked about how this is twice as big as this. So in other words, DG over BG relates by half. And it's true for all of the medians. They're divided up into half and double, right? 1-to-2 ratio. We proved that last week. We'll prove it again next week. For now, I just need you to know it. Let's go back and look at the perpendicular bisectors. What's the center that the perpendicular bisectors make?
90 degrees.
What center do they make?
I don't know. Circumcenter.
That's right. And the circumcenter is the center of what?
Oh, but I don't know.
What's special about the circumcenter?
It creates radii to vertices.
Mm-hmm. So it's this right here, from here to here, from circumcenter to Bailey-Leahy, will be the same as circumcenter to Jacob, the same as the circumcenter to Khalil. These 3 segments are all the same length. And if we have a bunch of segments that are all the same length sticking out from a central point, what do we really have? A bunch of lines that are the same length sticking out from a center point. We have a circle, don't we? Those are radii. So if I make a circle, notice how it hits all the vertices. It's because those are all the same length away, right? That's what a circle is. So when I connect it up, and I move the triangle around, right now it's acute. We know in a right angle triangle, where does the circumcenter go?
The vertex.
It goes to
Oh, the hypotenuse.
the hypotenuse, the midpoint of the hypotenuse. So what does that tell you about this?
It's the. I don't know.
What?
Between Bailey-Leahy and Khalil.
It's like the thing of the circle. What's it called?
Well, it's 2 radii put together, isn't it?
Yeah.
What do we call that? Diameter. Very good.
That's what I was trying to say.
So it turns out a right triangle inside a circle, its hypotenuse will always be the diameter. So if you put 3 points on a circle and it makes a right triangle, right angle here, then the hypotenuse will always be the diameter of the circle. There's a theorem about that we'll be learning later. But notice if I change this right angle around, like, here's what I'll do. I'll fix the angle. Let's see if I can fix it. Yeah, I won't worry about it right now. But if I fix that right angle, so it's always a right angle, notice how the hypotenuse will always be the diameter, right? So no matter what right triangle I draw in the circle, as long as the points are always on the circle, that hypotenuse will always be the diameter.
Even if you put it at the bottom.
Yep, because guess what happens? I don't have a triangle anymore. I have a straight line. But a slight variation makes it pop out, right? Triangle disappears. Right? You can't have a triangle if you only have 2 points. And if they're both the same, then you basically have 2 points. But yeah, right angle. Now, if I go from acute, right, to right, it's on the midpoint of the hypotenuse. What happens when I go obtuse? And that makes sense. Because an obtuse triangle, let me highlight my triangle so you can see a little bit better. Maybe on here. Alright, so there's my triangle. In order to make a circle that hits all those points, right? I have to draw a really big circle. So no wonder the circumcenter ends up on the outside. Connect all those up because they're so far apart because it's obtuse. I have to draw a really big circle. I can't do like this, right? Because that'd be an oval. So in order to make a circle, it's really big, which means the center is outside. When I have a right angle, and I know that's a right angle because the hypotenuse is the diameter, the circle's just big enough where the center ends up right here. And then when I go acute, the points are so close together. When I go acute, the points are so close together that I can fit a circle very easily around it, so the center ends up being in the middle, right, inside the triangle. So circumcenter for acute is inside, and then it slowly pushes to the outside. It goes through the 90 degree, right? Third one. And then on the outside, for obtuse, the in-center. Without looking, where's the in-center located when it's acute? Inside. What about right? Inside. What about obtuse? Why? Because the circle's inside. How could the center be outside if the circle's inside? Here's my circle. The center of that circle is here, right? Really bad at aiming, right? What about the medicenter or the centroid? What is its property? Center of mass. Will the center of mass ever be off the thing you're trying to balance? No, so it's always going to be inside, right? Cool. Angle bisectors. When they intersect. This is kind of the weird one, like angle bisector. Obviously, it's the thing that cuts the angles in half, right? But what's the center of the angle bisectors? The in-center. The in-center. Very good. Perpendicular bisectors form what center? Circumcenter, right? The really cool one. That's my favorite. It's also got the weirdest segments, right? Because it goes straight from the midpoint, just straight out, right? You get these weird looking lines all over the place. They don't go to any vertices. Orthogonals are kind of weird because they're just 90 degrees. What center do they make? Orthogonals, they have the orthocenter, right? And the only cool thing about the orthocenter is that it divides up the triangle into 6 similar triangles, each with a pair. They're not all similar to each other, but they end up being similar across. Let me show that on here. So see how these triangles are similar? And these ones are, and these ones are? It kind of divides the triangle in half into 3 triangles, and then their opposites over here. Notice the biggest triangle here ends up being similar to the smallest triangle there, and vice versa. In one way, it actually kind of like dilates them through to the point, like it shrinks it down and sends it through to the other side. Shrinks it down and sends it through to the other side. Shrinks it down and sends it through to the other side. Kind of what similar triangles are like. They have a dilation factor. Why do the orthogonals on a 90-degree triangle intersect with the right angle? Why does this happen? And that's the intersection point, orthocenter. Why is that the orthocenter on a 90-degree? What's another word for orthogonal? Perpendicular, right? It's the intersection of the perpendicular lines. Isn't this line perpendicular? Isn't that line perpendicular? Where do they intersect? Right there. Now, where's the other perpendicular that I didn't draw? Well, it's this guy, right? But if 2 of them intersect there, the third one has to, right, in order for them to be concurrent. Right? If I draw 2 lines and I have them intersect, and I say, look, I'm going to draw a third line. I'm going to make it concurrent. Where do I have to draw it? It has to go through what?
Right there.
That specific point. Because if I do any other point, it won't be concurrent. So if these 2 are already there, then the third one's going to be there as well, right? All right. Obtuse triangle. I'm telling you this is a center. I'm not going to tell you which center is it. What center do you think it is? Orthocenter. The height of this triangle is from here to here, right? So that height's going to go whoop. Flip it, it's going to go through there. That's the orthocenter. What if I told you this was a center? What center would that be? Perpendicular bisector center, which is the what center? Circumcenter, because it's the center of a circle that goes all the way around to these points. Beautiful circle.
Perfect circle check.
Right. Perfect circle coming to this. More unrealistic standards for women.
I really want to try
Yes,
it.
you did.
Like we could do six.
Okay.
The best way to make a circle is to do a right triangle. Have that be the hypotenuse, and then you know all 3 points.
I'm putting my sweatshirt in your closet.
This is what you need to know. You need to know what centers are what. You need to know what makes the centers, right? Angle bisectors, orthogonals, whatever. The special properties of them, like where the center is located, depending on which triangle we're talking about. Right? The in-center is the center of an internal circle, so it's going to create radii that go to the sides of the triangle. Why do they go out at 90 degrees? Well, because when we measure something, right, we're measuring the distance to the side of the triangle, right? We measure at 90. If I were to measure my head to the ceiling, I would measure like this. I wouldn't measure like this. Right? I'd be like, oh man, I'm like 35 feet underneath the ceiling because I'm measuring like this. Right? No, I measure straight up. Like a lot of you guys, when you stand back to back, you're like, I'm the same height as that person because you start measuring like this. Look, right? You go straight back at 90, or straight up if you're measuring to there. So when we're measuring this circle, right, the in-center, it's the same distance from every side of the triangle. So when I show that, the distance there is at 90. We're measuring towards that thing at 90 degrees. So those are 90 and equal because they're radii. All right, stop talking. The radii of this is going to be the vertices. How do I know that? Because the circle goes on the outside. So from the center to the circle is a vertex. You got to know all this stuff. We'll review tomorrow. Your quiz will be on Friday. Tomorrow I am going to show you some stuff that's a little new. That's not something we covered today 100%. It's just going to be the application of this stuff. So for instance, if I told you that this segment was 6, how big would BG be? All right, ladies, I will split all of you up because you're annoying me. We are approaching Danny levels. This would be 6 as well, right? So things like that is what we'll talk about. Don't forget that the centroid divides it up into 2-to-1 ratio. That's the tricky one that you got to watch out for. Go away.